Hello, everybody. Good afternoon. Let me make sure we're all good to go here. Chat, participants, cool. Make myself big. Great. There's some 17A log transformation in the background right now if you care to think about that. Let's see, let's wait a minute to make sure everyone has a chance to get here. I also wanted to request from everybody, I would love to see you on video. I understand if you don't want to be on video. If you're not going to be on video, I would love for you to put up a different picture, not just your name or the letter of your first name. It gets boring. So for those of you that have no picture or no video, find a new picture to put up. It can be a picture of you. It can be a picture of just something you like, something appropriate, please. So sometime before next week, I would like you on. In fact, I'm going to write myself a note. Maybe I'll make it like an assignment in Canvas or something. I don't know. But pictures on Zoom for everybody. Okay. I know someone also had asked me to make a video or two about what was it, tangent planes and stuff. So I did do that. It's on Canvas and YouTube. You should be able to see that if you're interested in seeing it. So I guess what should we talk about today? Any requests? Oh yeah, and before I forget, here's the link to the attendance form. Please go fill it out as usual.
Maybe today we can talk about the gradients. We went a little bit over that for Rodriguez's class.
Totally, we can definitely talk about the gradient. Yeah. Sure. So, yeah, why not? Okay. Sorry, I should erase this ahead of time. So the gradient actually comes up a lot in various places when you're talking about surfaces or multivariable functions. And it has it's very much linked to the idea or to the computation of partial derivatives. So before we start talking about the gradient, it'd probably be good to do a couple, at least one example of a partial derivative. I know we did a couple last time. Let's look at one more. Let's say our function f of xy is equal to, what do we got here? This is fairly straightforward. X cubed plus 2x to the fourth y to the fifth. Plus x over y. And I would like to find the partial in both the x and the y direction. And I'll remind you, when we're finding the partial in the x direction, right, we're keeping y a constant, so we're treating it like a constant, and its derivative acts like the derivative of a constant. So the derivative of x cubed, which is 3x squared. The derivative of 2x to the fourth times this constant is just 8x cubed times that constant. And the derivative of x divided by a constant is 1 divided by that constant. I'm really kind of thinking of this as 1 over y times x. So the derivative of a constant times x is just the constant times 1. I'm going to move this a little bit this way. So, great, there's our partial with respect to x. The partial with respect to y is equal to, well, derivative of x cubed is 0, because it's a constant. Now I've got a constant times y to the fifth. The derivative is going to be 2x to the fourth times 5y to the fourth. And this x times 1 over y, well, the derivative of 1 over y, or y to the negative first, is negative y to the negative second. And then the x, that's a constant multiple, just sticks around. So those are your partials in the x and the y directions, respectively. Now, typically when people talk about the gradient, they talk about calculating the gradient at a point. So for example, I could say like this function. So first let's look at f of, let's make it not too terrible. Let's look at f of -2, 1. So I'm going to plug in -2 for x and 1 for y. I'm going to get, let's see, -2 cubed plus 2 times -2 to the fourth times 1 to the fifth plus -2 divided by 1, which ends up being -8 plus 2 times 16 is 32 minus 2. So it looks like I've got about 22. All right. So kind of right too big here. So the gradient tells us, and Rodriguez said this in class, the gradient is kind of the best analog of the derivative in general. Right? The derivative of the x direction, the derivative of the y direction, I mean, that tells us something, but the gradient kind of combines those and writes them as a vector. So very kind of generally, the gradient of f, and I think that symbol's called nabla, I think it's N-A-B-L-A. I just say the gradient. So the gradient of f is a vector. So the gradient of f in this particular example is the partial derivative of x. And there's a couple ways you can write this. I like to write in the I direction plus the partial derivative of y in the j direction. You could also write this as a vector like a column. People write it like this. You could also write it as a vector like a row. Those are all perfectly fine ways of writing the vector that is the gradient. It just depends on kind of which way you prefer to write it. Okay, so now I could also find the gradient of that function. So I should say our example is going to be kind of not nice. Right? Our gradient here is, I'm going to write it like this, is fx, which is kind of gross, 3x squared plus 8x cubed y to the fifth plus 1 over y. That's the I, or the x component. That's going in the x direction. And in the y direction, we have this thing. I'm going to write this as 10 x to the fourth, y to the fourth. And we also have minus x y to the -2, or a minus x over y squared. So this is the gradient of our function. It's a vector evaluated at any point. And then, or sorry, yeah, at any point. And then we could actually evaluate the gradient at the point we wrote, which was 2, -1, I think. No, I think it was -2, +1. Yeah, it was. So just a notation thing here. All right, some people will write this as the gradient of f at -2, 1. Some people would write it as the gradient of f at -2, 1. They both mean the same thing. Sometimes it's just more convenient to use one notation over the other. So plugging in -2 for x and 1 for y, I'm going to get, well, on top I'm going to get, let's see, 3 times 4, 8 times -8 is -64, plus 1. And then on the bottom, I'm going to get 10 times 16 minus -2 over 1. So I end up with a vector that is, let's see, 12 minus 64 is -52 plus 1 is -51 over 162. So,
Is that, excuse me? Is that negative 51?
correct, yeah.
Okay, thank you.
So this actually tells us something which we haven't talked about yet. But what it actually tells us is at this point on our surface, if you go in this direction, that's the direction that's the steepest to go in, which is kind of interesting. So one thing I'm going to repeat often that you're going to want to remember is that the gradient vector at a particular value or particular point always shows you the direction of steepest increase or fastest increase. It's always true. Let's look at another example. I'm going to go back to my favorite example. Maybe not my favorite, but an easier example. So we're going to look at the downward opening paraboloid, which I've definitely used in this class already. 9 minus x squared minus y squared. It's very convenient. I'm not terrible at drawing it. It looks, I could actually draw it on the plane, I guess. Okay, 1, 2, 3. Sorry, I said I wasn't terrible at drawing it. Now I'm about to suck at drawing it. There we go. Okay. And it kind of does this little parabola looking thing. You can also do that parabola looking thing if you want it to come out at you. Okay, so there's the paraboloid opening downward, 9 minus x squared minus y squared. And we can definitely find the gradient of this function. So the gradient here, well, what's the derivative? So I suppose I should find the partials first. The partial with respect to x is negative 2x. The partial with respect to y is negative 2y. So the gradient is, I'm going to write it a different way this time just to kind of expose you to it. The gradient I can write as negative 2xi plus negative 2yj, where I is the x direction, or it's actually the unit vector in the x direction, where I is the vector 1, 0, or 1, 0, 0, and j is the vector 0, 1, or 0, 1, 0. This is just saying this much in the x direction, this much in the y direction. And then we could find the gradient at a point. For example, so on my surface here, I could look at the point, say 2, 1. So out 2 in the x direction, over 1 in the y direction, and then up. So if x is 2 and y is 1, and z is going to be 4, right? F of 2, 1 equals 9 minus 2 squared minus 1 squared equals 4. So here we are. Okay, I went out this way and then went over that way. So we're on that circle there. This circle, by the way, that's a level curve where z is equal to 4. Okay, so at this point, which direction on the curve is the direction of steepest descent? Well, it's not going side to side, because that would kind of just make you stay at the same height. And it's not going kind of out away from the origin, because that would mean you were going down. The direction of steepest descent here actually is going to be straight in towards the center. If I plug in the points, so again, this is the point here. 2, 1, 4 is that point there. If I plug in 2 for x and 1 for y, look what I get. I get the gradient of f is equal to the gradient of f evaluated at 2, 1. It's negative 4i minus 2j. Or if you prefer, the gradient at 2, 1 is the vector negative 4, negative 2. Same thing, it just is a different way of writing it. Now, if you think about it, I'm gonna draw this circle on the XY plane, meaning here's X, here's Y, and sorry, 1 second here. Gotta think for a second. And 4. Yeah. So here's my. Why am I dotting it? I don't know. So there's the circle where z is equal to 4. Right? I'm just drawing that circle in the xy plane. Here's my point, 2, 1, 4. Right? X is 2, y is 1, z is 4. And if I'm going in the -4, -2 direction, I'm going 4 to the left and 2 down, which means I'm going that way, straight towards the origin, which makes sense. If I'm here and I'm climbing up this mountain, the way that's going to be the steepest is if I go straight towards the origin, because the top of the mountain is at 0, 0, 9. So I know your teachers haven't talked about this aspect of the gradient yet, but it's kind of a key feature of the gradient. So that's why I thought it was important to mention. So whenever you find the gradient at a particular point, you're just finding the vector that tells you the direction of steepest descent. Now, let me see here. One more thing to say about this, because it's probably going to be true. Most of the time, when someone asks you for a direction vector, there's actually a lot of different possible answers, right? The vector -4, -2 is the vector in this direction. But you know what else would have been a perfectly fine answer? -2, -1. That is also a vector that goes in the same direction as -4, -2. It's just not as long. It's half as long. So how does your teacher kind of make it easier for themselves and ensure that everyone gives them the same answer, right? I don't want 10 different people giving me 10 different vectors that all have the same answer, but a different length or magnitude. So the way we say that we want our answer written is we want a unit vector that is in the direction. So neither of these are unit vectors because they both have lengths that are much longer than 1. A unit vector has a length of 1. To find a unit vector that's in this direction, you just take your vector and divide it by its own magnitude. So I'm going to erase this here. The unit vector in the same direction would be this vector, -4, -2, divided by its own magnitude. And the magnitude of the vector is just the square root of the sum of the squares of the component. So instead of saying divided by, I'm going to say multiplied by the reciprocal. So it's going to be times 1 over the square root of -4 squared plus -2 squared. Which, if we simplify, is just -4, -2 times 1 over the square root of 20. I know things are getting a little bit messy there. So that would be the answer that you would usually want to say is the actual direction vector for that. And I'm sorry, I can see some of you are like, what's he writing there? Sorry, let me write it over here. It's 1 over the square root of 20 times that. And you could probably simplify that further, but we don't really need to at this point. I know Rodriguez was talking about the unit vector, sorry, not the unit vector, the gradient as it relates to finding the tangent plane. So let's kind of talk about it. In fact, why don't we look at this example here and say, I want to find the equation of the tangent plane at this point. So there's some plane here, probably kind of just, I can't draw it. I would try to draw it, but it's not going to work. So the way we would find the tangent plane, which would look maybe something like that, I don't know, right at that point there. It's covering up. Well, as I said in the video I made yesterday, which I definitely encourage you to look at because there's some other examples that are worthwhile, I think. The way you find the equation of the tangent plane or the linearization of the function is kind of the same thing, is exactly like the way you find the equation of the tangent line to a regular function or the linearization of a function. So just like in 17a when we did linearizations, or 9, it was something like the linearization of a function is f of a plus f prime of a times x minus a. Or they might have used x naught here. They might have done f of x naught plus f prime of x naught times x minus x naught. Right, that's just the equation of the tangent line. In fact, let me draw the picture here. That's f of x, and that's the point x naught, y naught. Ooh, sure. If I'm trying to find the equation of this tangent line, why not find the equation of the line? It's y equal to mx plus b, or preferably point slope form, y minus y naught equals m times x minus x naught. But I know what the slope is, or at least I know how to find the slope. The slope of a tangent line is just the derivative of the function evaluated at the point. So here the slope of this red line is the derivative evaluated at x naught, right? That's x naught, that's y naught. So we get y equal to y naught, or I'm adding y naught to both sides, plus m times x minus x naught. And then we can replace y naught with f of x naught. So I've got y equal to y naught plus m, which is the derivative. And here's the great thing, and great, maybe debatable. Here's the nice thing about tangent planes and linearizations of two-dimensional, of functions of two variables. It's almost exactly the same as this. You just have to throw on kind of the extra piece. So, never enough room. So for a two-variable function, say like f of x, y, the way the linearization works is, well, it's the function value plus the derivative in the x direction times x minus x naught plus the derivative in the y direction times y minus y naught. So there's just kind of like an extra little piece. So the linear, I'm gonna write it down here because it's where I have room. So for f of x, y, if we're going to find the linearization, aka the tangent plane at x naught, y naught, here's what we're going to get. It's going to be L of xy equal to f of x naught, y naught. Just like we have, I meant to write f of x naught here. Sorry. Same difference. I actually wanted to write it. So right, just like we have f of x naught here, we have f of x naught, y naught there. And then we have a small change in x times the derivative. So I'm going to have, again, a small change in x, but now it's times the derivative in the x direction, right? That's the partial with respect to x. And I'm going to, this is where it gets kind of messy. I'm going to write it as fx evaluated at x naught, y naught times x minus x naught. And then the same thing in the y direction. fy evaluated at the same point, x naught, y naught, times y minus y naught. And it's a little bit unwieldy, right? It's kind of a messy formula. And at least Rodriguez, does he go by Rodriguez? Does he go by Simmental? I don't know. If someone wants to tell me, I will try to say the right thing. Whatever. He said there's a nicer way to write this, and there is, or this is a more compact way to write this. So notice the partial with respect to x and the partial with respect to y, those are the components of the derivative that is the gradient. So you can write this as f of x naught y naught plus this vector f, the partial with respect to x. I'm going to write it this way. Evaluated at x naught y naught. The partial with respect to y evaluated at x naught y naught. Dotted with the vector x naught, x minus x naught, y minus y naught. That's the same equation, but this thing here, this vector fx, fy, that is just the gradient evaluated at x naught, y naught. So just, some black dust all over my hands here. So just to make sure everyone's okay with that, so the dot product, I'll remind you the dot product really quickly. For two vectors, if you say like, say you have the vectors 2, 3 dotted with 4, 1, the dot product of two vectors is just multiplying the corresponding components together and then adding all the results up. So this would equal to 2 times 4 plus 3 times 1, which would just be 11 in this case. It's just an example of the dot product. So that you can see that, oh yeah, down here, when you're dotting this vector with this vector, you're getting the partial with respect to x times x minus x naught, just like we have here, and then plus the partial with respect to y times y minus y naught, which is what we have over here. So this is a way you could use the gradient to compactify this equation. I don't think you need to do it that way. I probably, if I was doing a linearization of a function of two variables or a tangent plane, same thing, I would definitely probably just remember this. Okay, so I know we actually had a real function with some real numbers that we started out with here. So let's go back to the other side and talk about the function and finding its tangent plane at the point. Again, don't hesitate to say something if you have a question. So if I want to find the equation of this tangent plane here, well, it's going to be L of x comma y as you generate the linearization. And it's going to be f of x naught y naught, so f of 2, 1 plus the partial with respect to x evaluated at 2, 1 times x minus 2 plus the partial with respect to y evaluated at 2, 1 times y minus 1. So all this ends up looking like is, let's see, so f of 2, 1, that's just 9 minus 4 minus 1, which is 4. Negative 2 x evaluated at 2, 1, I'm just going to plug in the 2 and get negative 4 times x minus 2. And then negative y evaluated at 2, 1, I'm just going to plug in y equal to 1 and get negative 2 times y minus 1. And that's the equation of the tangent plane at that point. And while you could simplify this, or you could totally multiply it out, you get 4 minus 4x plus 8 minus 2y plus 2, and write it as negative 4x minus 2y plus 14. We usually don't. And well, I mean, I don't know about usually. So we sometimes do. Also, for anyone that came in late, here is the link to the Google form to mark your attendance, if you will please do that. And get used to doing it. We're going to do it every class, so just get used to being in class. Oh yeah, there's a link. If I forget, you guys should remind me so that I get it up there because it's important. But the reason we might leave it like this instead is because, well, if you remember back in 17a, we used linearization sometimes to approximate a function value at a harder to evaluate point. Like you might have used, and this is the example I did on YouTube. If I was going to try and approximate, like, I don't know, the square root of 10, I think I did. No, I think it's something else. You would use a linearization of f of x equal to the square root of x at the point 9, because 9 is really close to 10, but it's much easier to evaluate. So someone could say, use a linearization of this function at the point 2, 1 to approximate f of, what have I got here? 2.03, 0.99. And while we certainly could do that, just actually evaluate it, right? You could totally plug in 2.03 for x and 0.99 for y and square them both out and add it up, and it wouldn't be too terrible. It's not super duper easy to do by hand, but if I actually plug these values into this linearization, it's going to give me a point on the tangent plane that's very, very close to the point that's actually on the surface. And if I do that, I'm going to get, let's see, so that's going to be approximately L, the linearization, at 2.03, 0.99. And while I could totally plug it into this equation here, I'm actually going to, it's actually easier to plug it in here because here it's easier to see. I'm going to get 4 plus -4 times 2.03 minus 2 is just 0.03. And a -2 times 0.99 minus 1 is just -0.01. So you can kind of see how each of the different slopes in the x direction and the y direction are contributing to kind of how much error there is or how much we're off by. So I end up with 4 minus 0.12 plus 0.02. So I end up with, I think, 3.9. If you compare that to what you would actually get with a calculator, if I did, let's see, 9 minus 2.03 squared minus 0.99 squared, I end up getting 3.899. So pretty good approximation, but I would use a calculator. All right.
Could you explain how you get the slopes of the -4 and -2?
Totally.
From
So the way I'm getting those slopes is I'm using, so for the x part, I'm using the partial with respect to x, right? That's just, so right here, this part here, that is just f sub x, right? And over here, that is just f sub y. And then I'm plugging in the values of x or y at the point I'm using. So I'm using the point 2, 1. So that's how I'm getting those values.
Okay. Okay. Thank you.
Other questions?
James?
Yeah.
So for the linearization, I can't see it well. So after the parentheses -2x times, is that x minus 2 or?
Oh, sorry. Right here? Here?
Up?
So yeah, so it's f of 2, 1 plus -2x evaluated at 2, 1 times x minus 2.
Okay.
Plus -2y evaluated at 2, 1 times y minus 1.
Okay.
So it's always
Thank
x
you.
minus the x coordinate and then y minus the y coordinate. Other questions about this? What else do I want to say here? So you can definitely do another example if you want, but there is another thing. So I was looking at the notes from Rademacher's class. Again, no idea if I'm saying his name right. By the way, just a reminder, you all know you're being videoed, and this video is going to be available on YouTube. So what was I going to say? I mean, I can't imagine anyone's watching these videos who's not in this class, right? I couldn't imagine who would want to. Sorry. Oh, the other thing I was going to mention was, so there is this idea of the chain rule for multivariable functions. And where'd you go here? So let's say, yeah. Well, there's also that. That's cool too. All right. So let's say we have. This is not what I want. I want this other page I've got over here. Sorry, 1 second. So let's pretend, and I think, yeah, let's say I have like f of x, y is equal to, I don't know, x cubed plus y squared plus e to the x, y cubed. But there's actually a parameterization where x and y are both functions of t. So say like x of t is equal to t to the fourth plus 1, and y of t is equal to sine of t. And what I really want to find is the derivative of this function with respect to t. Now, there is a long way I could do it. I could totally substitute in this for each x and this for each y, and then just take the derivative the long way using the product and the chain rule a bunch of times. But there's kind of a nicer way of doing it. So there's this thing called, I don't remember, I think it's called like a, I don't remember what it's called. You can draw the paths, is what I think it is. So f is a function of x and y. So you draw f at the top and then the things it's directly a function of below it. And then x and y are both functions of t. So if I want to find df dt, the derivative with respect to t, it's all of the paths that get me to t added together. So there's a path that takes me from f to x. That's del f del x. There's a path that takes me from x to t. It's dx dt. The reason I'm saying del here is because it's a partial derivative, because f is a function of more than one variable. The reason I'm saying d here is because x is just a variable of t, a function of t. So I don't have to say del, I have to say d. Similarly, and then there's also the path this way, where f to y, I have to do the derivative with respect to y, so the partial, and then y to t, I need the derivative, y to t. So what it ends up looking like is del f del x times dx dt plus del f del y times dy dt. Let's calculate it. It's going to look weird at first. So del f del x is just the partial with respect to x. It's 3x squared plus 0 plus e to the stuff times the derivative of that stuff with respect to x is just 1 times y cubed times dx dt, the derivative of x with respect to t is 4t cubed plus del f del y, so the derivative of this with respect to y, which is 2y plus e to the stuff times the derivative of the stuff here is 3y squared x. Again, if I'm differentiating with respect to y, I've got a constant times y cubed. The derivative is the constant times 3y squared times the derivative of y with respect to t, which is cosine of t. Finally, my answer should actually only have the variable t in it. So I'm going to go back, and this is where it's kind of the tedious part. I'm going to replace every x with t to the fourth plus 1 and every y with sine of t. So my final answer here is going to be gross. It's going to be 3 times t to the fourth plus 1 squared, right? That's my x. And then plus e to the t to the fourth plus 1 times sine cubed of t times sine cubed of t times 4t cubed. That is all of that. And then plus, hope I can fit this in here, 2 times sine of t, right? Y sine of t, plus e to the x is t to the fourth plus 1. Y cubed is sine cubed of t. Times, I think, oh, sorry, times 3 sine squared of t times x, which is the t to the fourth plus 1. All of that times cosine of t. So that's how you take this derivative using the chain rule. It's kind of neat. All right. I feel like there was something else I wanted to mention. Do you guys have any questions you want to ask? Okay.
James?
Yeah.
For just like a quick refresher, can we go over the derivatives of logs and exponents again?
Definitely.
Thank you.
It's really, actually, it's a good thing to remind yourself of because they definitely come up a lot. And they're easy to kind of forget. I will also just throw it out there as usual. If you would like to see me make a video on something else, like tangent planes that I forget who asked for, I think it might have been Nicole. I'm happy to do so. You just have to let me know what you want to see. So derivatives of e to the x and stuff. Also, one last time, I'll throw the attendance link up there. If you haven't already, please go fill out your information on the attendance link. All right, so there's kind of like 8 things to say when it comes to the derivative of logs and exponentials. Here are the beginning things. The derivative of e to the x is e to the x. And the derivative of the natural log of x is 1 over x. And then there's the chain rule version of these formulas. So if the derivative of e to the x is e to the x, the derivative of e to the stuff is e to the stuff times the derivative of stuff. For example, the derivative of e to the x cubed plus 1 is e to the x cubed plus 1 times 3x squared. In a similar way, there's a chain rule version. There's always a chain rule version for everything. Right? If you know the derivative of a function of x, you also know the derivative of that same function of some more complicated stuff. It's just the same rule, but then at the end you have to multiply by the derivative of that more complicated stuff. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Oftentimes, people will put the derivative of the stuff on top of that fraction. That is perfectly normal and what I would usually do. An example here would be the derivative of the natural log of, I don't know, sine of x plus x to the fifth. The derivative would be 1 over sine of x plus x to the fifth times cosine of x plus 5x to the fourth. Or you can write it as cosine of x plus 5x to the fourth over sine of x plus x to the fifth. All right, and then we're going to repeat all of these except for logarithms with a different base, so a non-natural base. For example, the derivative of, I'm just going to use the general a to the x is a to the x times the natural log of a. I will point out when you're talking about exponential functions and logarithmic functions with other bases, we are always assuming that the base is positive and not equal to 1. You should normally just think of regular natural numbers. So like 2 to the x, or 3 to the x, or 4 to the x, or 7 to the x. Anything like that is normal, or log base 5 of x, or log base 8 of x. You shouldn't have any negative numbers. You shouldn't have any, actually that's it. You shouldn't have any negative numbers. You shouldn't have 0. You can have weird irrational or fractional numbers. We usually don't. Like you don't really see log base 2/3 of x, but you could. So an example of this would be the derivative of, say, 2 to the x is just 2 to the x times natural log of 2. And then for logarithms of a different base, instead of multiplying by the natural log of the base, you end up dividing by the natural log of the base. So the derivative of log base a of x is not just 1 over x, it's 1 over x also with a natural log of a in the denominator. So one thing I've noticed that's true for exponentials and logs of different bases is the exponentials of the different base, you always multiply by the natural log of that base. For logarithms of a different base, you always divide by the natural log of that base. Always true. An example here, I feel like I'm going to run out of room, would be the derivative of log base 2 of x. It would be 1 over x natural log of 2. All right, finally, the chain rule version of these formulas with different bases. So the derivative of, say, like a to the stuff would be a to the stuff times the derivative of the stuff times the natural log of a. Right? There's that additional extra little piece of the natural log of a. So for example, the derivative of 2 to the x cubed plus 1 would be 2 to the stuff times the derivative of the stuff times the natural log of the base. I will point out, this formula also works if your base is e. It's just that the natural log of e is 1, so we don't end up having to write that part there. But you could always use this longer version of the formula, and it will always work. It's just when your base is e, we kind of like, oh, we don't need it. Same kind of thing over here. Hopefully I can fit this in. The derivative of log base a of some stuff, I'm going to write it the shorter way. It's 1 over your stuff times the natural log of a in the denominator times, I can write it this way, the derivative stuff. So I really think of the natural log part coming last. So I'm thinking of this as 1 over the stuff times the derivative of the stuff times 1 over the natural log of my base. It doesn't really matter what order, it's just the order I think of it in. An example of this would be, let's make it a little bit shorter than that one. Let's say the derivative of log base 3 of x squared plus 1. The derivative would be 1 over my stuff times the derivative of my stuff times 1 over the natural log of 3, which if I simplified would look like 2x over x squared plus 1 in parentheses times natural log of 3. All right, so those are the log and exponent differentiation rules, and that kind of is really all of it. Sorry, it's hard not to make faces when you're on video. Like, oh yeah, I can make faces. Anyway, also, did you guys see my cool Gaston mug? Pretty fun. Got it at Disney World. I guess that's about it for today. I will say, what's the thing I was going to say? If you want to see things, let me know. Friday, come with questions. I'll try and look and see if you guys have any upcoming quizzes. Oh, I know what I wanted to ask. Are any of you having to like do quizzes for your class on Gradescope where you're entering mathematical typing? You can give me a yes or a no in the little thingy over here if you wanted to. I'm guessing the answer is no for most of you, or probably for all of you, but I saw some students in my other classes were having to do that, and it can take a little bit of learning first. Okay, so it looks like a no for everyone who's answering, which is fine. If that changes, if you see your teacher asking you to do stuff in Gradescope where you're typing in math and using like backslashes and dollar signs, if you see backslashes and dollar signs, let me know. I can totally show you guys how to do it. It's not that hard, but it does take a little bit of practice. All right, I think that's it for today. I will see you all on Friday. Take care. There's the bottom of my face. Bye.
Thank you.
Welcome. And make sure you fill out the attendance. I'll say it like 1,000 times.
I think I did already.
Good, good. I'm sure you all did.